All right, before we move on to getting into contraction and the cross bridge cycling, let's look just a little bit more at this excitation-contraction coupling. So this graph is a tracing of membrane voltage changes that occur when an action potential has been initiated at the neuromuscular junction. This occurs in milliseconds and results from the opening and closing of those sodium and potassium gates in the sarcolemma. So look, we've got 1, 2, 3, and 4. Goody, goody. That corresponds with 1, 2, 3, and 4 here. So here we've got minus 90 millivolts, minus 65, 0, and positive 30 over a period of time in milliseconds. Okay? So, number 1, the muscle cell membrane, when that cell is not being stimulated, is polarized with a resting membrane potential of minus 90 millivolts. If this cell is being stimulated by acetylcholine binding to those receptors and sodium ions flooding in, this is going to move us to step 2, where the end plate potential is reached, which means we have reached minus 60 millivolts as those sodium ions are rushing in right here during number 2. So it moves the voltage from minus 90, so nothing's happened here, resting membrane potential. Depolarization is occurring starting here. We are bringing in sodium ions and the cell is becoming less negative, less negative, less negative, less negative. And bam, when we got enough sodium in to reach negative 65, this cell is now depolarizing all the way to positive 30 and contraction is occurring. Now, in order to reset, we have to repolarize, which means pump the sodium ions out. Well, that means we're becoming less positive inside the cell. Less positive, less positive. Now we're moving into negative and negative and negative. There's our threshold, minus 65, but we're not back to resting. We got to get all the way down here to negative 90 millivolts to fully repolarize and reset. All right, let's pick up again where we left off a while ago. So if you remember that previous image that I showed you a couple of slides back, we had 2A and 2B. Well, here's 2C. This is actually all together over a 2-page spread on page 340 and 341 of your textbook if you're using the textbook assigned for my class. Okay, so let's move right back in. So when the action potential reaches a triad, now we mentioned this previously, but remember the triad includes a T-tubule, remember that's still muscle cell membrane, and the 2 enlarged areas of the sarcoplasmic reticulum that are on each side of the T-tubule. These are called terminal cisternae, or the end where we store stuff, right? So there's lots of calcium stored right there in those terminal cisternae, but really all throughout the SR, but a lot of it here in these enlarged areas, okay? So just reinforcing where we're at. Okay, so when that action potential reaches the triad, that is the T-tubule 1, 2, 3, and the 2 terminal cisternaes. So when it reaches there, it stimulates the conformational change. That simply means change in shape of voltage-sensitive calcium channels within the T-tubules. Now, once these change, it changes the shape of these little channels in the sarcoplasmic reticulum. Well, that's basically opening the calcium gates. So if you think of the calcium as being in prison over here in the terminal cisternae of the SR, when the gates change shapes, the prisoners escape. Now the prisoners are running around everywhere trying to get away from the prison. So what they're going to do is move out into the cytoplasm of the cell, and they're going to go searching for the myofilaments known as actin and myosin. So the calcium is going to hook up with one of those, and that's where we're headed next. All right, let's orient ourselves here at what we're looking at. So the green down here is myosin. Here's a myosin head. The purple balls are actin, okay? The red is your tropomyosin. Trop is the rope. And your troponin are the little proteins. Do we even have, there we go. So your troponin is the yellow here. I call that the anchor. It anchors the rope over the binding sites, okay? So the calcium that's released from the sarcoplasmic reticulum binds to the troponin. Look at there. Now that causes the troponin to roll the tropomyosin off the binding site. Once that is exposed, the binding sites on myosin want to hook up with the binding sites on actin. And that will form the cross bridge, and that is where we'll begin the next video.